Good afternoon again, and I hope you had a nice lunch or a coffee or just a discussion with your fellow colleagues. We are returning back to our sessions, right? And yes, this is a cozy databases room or databases corner, and the next presentation is no exception. And with this, I'm glad to invite on stage Evgeniy Ivanov from Yandex. Who will, in a moment, present about the aspects of high performance and scalability of YandexDB, right? The stage is yours.
Здраво, добро дошли. Всем привет. I'm very happy to see you here. And my name is Evgeniy. I work at YDB. And I'm very passionate about software performance. And this talk is purely about software performance, and I hope you will enjoy this talk and you will enjoy this topic as I do. You know that database, as you know, database choice is very extremely important, because a wrong choice might cause a real strong disaster in your application. You can lose customers' data, your expenses increase, and you, at the end, you will finish struggling with low performance and inability to scale, and it's a nightmare. In this talk, I will explain you why distributed databases are highly available and have extremely great performance. Also, I will show examples where YDB performs really well and scenarios where you should consider using YDB. And we will talk about interesting technical aspects behind YDB's high performance, and these aspects are applicable to almost any software and any database, and they might be very useful to you. First of all, YDB is open source. You can try it for free. You can change the code. Originally it was just OLTP database, but now OLAP support is coming soon. We are a very mature system. At Yandex, we have installations, we have clusters with thousands of servers. Please feel free to go to GitHub and start our page. First of all, YDB is strictly consistent. It means that in CAP theorem, we choose consistency. Trust me, in practice, it is the only right choice for you. We do serializable transaction execution, which practically means that it helps to avoid very subtle bugs in your application code. And it also helps to simplify your application logic. We are highly available and fault tolerant. We support multiple availability zones. Usually, availability zone equals to data center. And there are terms: failover, failback, recovery. In YDB, everything happens smoothly, automatically under the hood, without without requirement for human interaction. Consider example: you have a 3 data center setup, and one data center fails. Also, a rack in another data center fails simultaneously. YDB will be read-write available, which I find exciting. It makes YDB a mission-critical database. Some systems promise you to work 365 days, but at YDB, we take into account leap years. So when needed, we can work 366 days with zero maintenance window. Let's define performance. There are 2 key aspects of performance: throughput and latency. Throughput is the number of requests per second which database can handle, and latency is about request duration. Here we consider latency on client side. It's full duration from user perspective. At YDB and in this talk and usually in our benchmarks, we are focusing on achieving max possible throughput, limiting latency to 50 milliseconds on 99 percentile. Performance has no goal, only a path. Because every year you get new hardware, new algorithms, new applications, and challenges. It is the path with never-ending improvements. It's like lifestyle, I would say. I suppose that most of you here are software developers and application developers, and not database developers. So for you, performance is important because it saves your money. It saves money of your companies. Because the better database performance you have, the less hardware you need. Also, high availability and scalability are very important for a business because with highly available system, you can earn more. Let's start from, now I would like to introduce you performance tips and tricks which might be useful for everybody and applicable to any software you develop. The source of these tips is our own experience, is our own performance path. As you see, in just several months, we were able to double our throughput, keeping latency low. We done it making a lot of flame graph sessions, a lot of experiments, and we found some useful system configuration tweaks, but they are simple but yet powerful. And also some interesting bottlenecks, and I will share you examples of patterns and anti-patterns which might be useful for you. First, let's start from this picture. It's H-top. As you see, CPU is completely exhausted. System is kind of overloaded. You might think that it's impossible to increase your system's throughput. That is completely impossible. Because my colleagues and I originally were sure that it's impossible and we should maybe improve our code. But we found the solution. And solution requires no code changes. You execute same binary. It's applicable to any multi-threaded software and any database. You know that CPU caches are crucial for performance. And there is important metric, instructions per cycle, IPC. This metric is very tightly coupled to CPU cache efficiency. And to increase CPU cache efficiency, you might want to consider pinning threads to a subset of CPU cores to avoid migration of threads between cores. And solution is simple. It's called CPU affinity. You simply can use CPU sets or task sets to define CPU affinity of your process. And in our case, we got throughput increase by 20–40% with exactly same CPU consumption. And this improvement is absolutely proportional to improvement in IPC metric. So when you do analysis of your software, you might want to check IPC metric and to use it when you do improvements. In this picture, I show you results of YCSB benchmark. We will talk about YCSB later, but here I want you to see that with task set, everything becomes better in our case. Each execution has better throughput with task set than executions without task set. Another option is also simple. It's called huge pages. As I told, and as you of course know, cache misses are expensive, and TLB misses are even more expensive. Solution, transparent huge pages. It gives a modest improvement, extra 3% of throughput, but for free. You just simply turn on it in Linux configuration, and you get this improvement, and you do nothing, almost nothing for this improvement. Now I would like to continue with patterns and anti-patterns. But at first, I should to introduce you our actor system. Our actor system is a concurrency module and used in YDB. Actor is single-threaded entity with own state, and it's very simple. It receives messages, it sends messages, and it creates another actors. it's a very, I would say, it's extremely simple module, but yet it's very powerful multi-threaded module. Now consider example from YDB. You have queries, and here I show you actors which do query processing, and you have key value storages. All they are actors, and they send and receive messages. There is traditional approach called pushdown. Query processor prepares the program and sends this program to key value and asks it to execute the program. It helps a lot when you have filters, when you have complicated predicates, but what if you have just a simple key value load? Program execution takes longer than simple key value operation. And the problem is that load distribution is uneven. Recall Pareto principle, also known as Zipf distribution. A small subset of key value storages will handle almost all requests from query processors. It makes requests to key value actor latency bound. If we move back the program execution back to query processor, key value operation becomes simpler, it can be executed faster. Throughput increases, everything becomes better. So in some cases, a good pattern might be anti-pattern and cause performance bottlenecks. Besides that, you have a lot of compiler magic. We tried profile-guided optimization. It wasn't on the YCSB slide with the results. It gives from 20 to 30% of extra throughput for free. Also, there is post-link binary optimizer. It's just 3-5% of throughput. And link time optimization, it gives just 1-3% of throughput. But in common, just imagine you have a program and there are different ways to compile it. If you compile it properly, you can get much higher performance than you would have otherwise. Also, there are a lot of architecture, platform, and features behind this high performance. Unfortunately, we don't have enough time to discuss it deeply. I would like just to highlight some of them. And I leave links on the slides, and at final slides there will be a link to the slides, to these slides. So after the conference, you might want to check our talks about these features, about their development. It's very interesting technical topics and technical talks. Unfortunately, most of them are in Russian. First of all, we have separate compute and storage layers. We have own storage layer which works directly on the disks. We don't have file system between YDB and disks. We work directly on the disks, which in many cases helps to improve performance. We have own advanced actor system. There is a very interesting talk about its evolution. And YDB is written in C++, which also helps to achieve better performance numbers. And we have features like MVCC, multi-version concurrency control. They are also about performance, and you might want to check the talk. And I want you to remember that we are beyond Kelvin. Originally, YDB was based, I would say, rather was inspired by Kelvin ideas. But now we are not Kelvin, we are something else. And we are based both on good theory and good practice. Now, let's continue with benchmark results. YCSB is a very popular key value benchmark. Originally, it has been created for key value NoSQL databases, but it's loved by everybody, and it's widely used by distributed databases. It supports almost all modern databases, key value, distributed single server databases, almost everything. And we believe at YDB that it's impossible to do distributed transactions well if you can do simple key value load well. YCSB includes different workloads which represent almost any possible scenario in production. It has update heavy workload, read mostly workload, read only, read latest, read modify write, and also read workload with short ranges. It's almost all possible cases in productions are listed here. In our test setup here, we use clusters with just 3 but powerful nodes, powerful servers. Each server is 128 cores. It has 4 NVMe disks, 500 gigabytes of memory, and high-speed network. We compare against well-trusted and trusted and well-known distributed databases with CockroachDB and YDB. There are many rumors behind this comparison and behind this work which we did comparing our systems. And I'm here to tell you the naked truth. We didn't have a bar fight with them. It wasn't even like this. We didn't play muscles in a bar. Everything was done in a very calm atmosphere. We shared our findings, which I think a best way to compete, to make every system better, to discuss things, to discuss setups, results, so that everybody can benefit from the competition. So let's start from a moderate number of moderate-sized data set, just 300 gigabytes. As you see, YDB outperforms almost in all workloads, except workload A, which is write heavy, and workload E. Let's check what will happen if we increase data set size, and now it's 2 terabytes of data. Now YDB significantly outperforms every database except workload E. Maybe we have latency issues, or maybe we have worse latency because there is a trade-off between latency and throughput. So here are latency numbers. As you see, latency is great in just tens milliseconds, and everything is okay. So now you might have a question. Is it a silver bullet? Is YDB a silver bullet? It's a fair question. We work hard to make YDB best in all possible scenarios, but unfortunately, the work is not yet finished. So let's jump to analysis. First of all, especially because you're application developers, most databases provide different options to update rows. There is update operation, which is a read-modify transaction under the hood, and there is upsert operation, which is a blind write. As you might guess, blind write is significantly faster than read-modify transaction. And CockroachDB implements YCSB using update operation, which is slower. That is why in workloads A, B, and F, they are significantly slower than YDB and YDB. Let's check what's happening with YDB. We found 2 serious issues in YDB. First issue is about bare metal. YDB unfortunately failed to scale horizontally on a bare metal. Because you simply can't run 2 T-server YDB processes on a single node. Another issue is with vertical scaling. One T-server can't consume all the CPU resources. So you have just one T-server, it doesn't consume CPU, and throughput is low. We reported these issues to YDB team. They confirmed they have these issues, and they are going to fix them soon, and it will be really interesting to do measurements when they release the fixes. Workload C is exactly the same in all 3 databases, and as you see, YDB here also significantly outperforms other databases. Unfortunately, we still lose in workload E because we found a performance bug in implementation. And we are going to provide fix very soon in upcoming YDB release. So YCSB conclusion is the following. You should be, as application developer, you should be very careful when you implement your application, independent on database choice. YDB, we strongly recommend YDB for read mostly and read only workloads. But still, if you have a write intensive workload, it shows good results. You might want to check full YCSB report. The link is on the slide. Now, you might ask me, where are other databases? Why we don't compare about something traditional like a big elephant in a very tight car? You should first, before asking this question, you should ask your database vendor some questions. What will happen if something fails? Disk can fail, server can fail, data center can fail. Also, what about having clients located far from your data center? Can you easily improve their latency? Because it's about network, it's not about your database. And what will happen if your data set exceeds 500 gigabytes? Will your database work properly and show good performance? There are also big data questions, because we work at Yandex. Can you store a petabyte of data? And can you handle more than 100 gigabytes per second of data updates? Here is Donald Knuth, and he says, the best theory is inspired by practice, and the best practice is inspired by theory. And there are theoretical reasons behind high performance and advantages of distributed databases. And distributed database theory is based on the best practice, and I'm going to shortly introduce it. What in general do we expect from database? AC transactions. Of course, transactions should be durable, they should be atomic, consistent, and isolated. No questions. Scalability, maintainability, high performance, security, reliability, and fault tolerance, and availability. But nothing is reliable in this world. You have software bugs, you have hardware bugs, you have hardware faults, you have unreliable networks. It makes single server database not reliable and not available by its definition. I have a cool story for you from my own career experience. I worked in a fintech company, and we had a client with single server setup. One day, bored data center worker, he was just simply bored and decided to have some fun. And fun is riding shopping cart inside data center. He crashed into the server, and our client was disconnected from markets. They were not able to trade. Why? Because of software? No. Because of hardware? No. Just because of data center guy riding shopping cart inside data center. Are you sure you want to use single server setups after the story? So some single server databases provide you some possible solutions. Is replication a solution to use single server database and make it reliable? There are two types of replication, sync and async. Async replication has risk of data loss. It's usually not durable. And there are stale reads, data anomalies, and you will need to fight with them in your application logic. And trust me, normally you will finish with very subtle bugs which are hardly reproducible. In general, you should avoid async replication until you really know what you are doing. My private opinion, it's not my company's opinion or YDB opinion, but in many cases, async replication is a crime. There is sync replication, and sync replication is a way better, but still there is only single leader. It means that you can split only reads among replicas. You can't split writes. And when you have sync replication and single server database, now you have a separate load balancer, a separate failover and failback, and usually failover and failback requires separate consensus cluster, like Zookeeper, etcd. And behind this, when fail node is back, recovery might take a long time. Also, you still have a problem with scaling writes. Here I show you vertical scaling versus horizontal scaling. You see IBM mainframe, and you see a small subset of typical YDB cluster. I think typical YDB cluster is better, in my opinion. Sharding is solution for writes. Now, if you use sharding, you have horizontal scaling, you have geographical scaling, and now you have many leaders, many leading shards, or also so-called partitions or tablets. But there are sharding pitfalls. Now you have a problem with consistency. You need to read from multiple shards consistently. You have to implement distributed snapshots, and it's complicated. Also, you need a coordinator, when you have coordinator, of course, you need a standby and failover procedures for the coordinator. So everything becomes really complicated and kind of ugly. Now you have the choice. Do you really want to maintain a database with a separate load balancer, consensus cluster, failover and failback, coordinator, or do you want to use distributed database where everything is implemented under the hood and it simply works? So now it's time for conclusions. First of all, there are ways to ruin performance on the application level. It's kind of obvious, but it's independent on database choice. You might choose a good database, but write bad application. Or you might choose bad database and write good application to hide the problems with the database. Centralized or single server SQL databases doesn't match mission critical data by definition. And distributed database is the proper solution for availability and scaling challenges. And if you consider using distributed database, I believe you should, you might want to consider using YDB. Thank you for your attention. Now please ask your questions. Also feel free to hit me up after the talk or after the conference. There are contacts on the slide. So I will be glad to talk about databases, performance, maybe aerial photography if someone wants, almost anything. Thank you for your attention again.
Excellent. A round of applause, please. And now we move. I haven't even yet announced that we're moving to a question session, and we see hands already. Excellent. But before that, please note and provide the feedback. You have a QR code. You also have this application, which you can find out via QR code in your ticket booklet. Please provide the feedback. This is really important, and the program committee pays attention to that. Right, questions then. So I saw the hand over there, so right there in the center, please.
Thank you for your talk, and have two questions. The first one is, you mentioned that you use thread pinning, I guess. So I remember that you pin something to a core, and if it's a thread, are your actors pinned to your threads so that this optimization would actually work? And if yes, shouldn't be there a problem if there are uneven distribution of actor consuming CPU, if they're like some hot actors and cold actors?
Okay, thank you very much for an interesting question. In this particular case, I mentioned pinning threads from a particular process. Because we have too many cores, we start multiple YDB instances. Because we want to scale horizontally, and we design our system to be run on small number of CPU cores. We test this scenario. So in this particular case, each node had one process for storage, also known as a static node, and 4 processes of compute. And we used CPU sets for compute processes. So we simply split 128 cores between these 4 processes. And we isolate that helped to isolate threads from one process of compute from another one. So answering the second part about actors and pinning threads to particular core, I'm not sure that we try to start actor on the same core, but I'm not sure how efficiently it's currently done. But the best, of course, is to if you have a thread, if you have an actor, to start it on exactly the same core to increase the performance.
Okay, thank you.
Excellent. Right. Any other questions from the audience? Well, I can understand that it's close to lunchtime, right? Not enough coffee, but you can win a prize for asking the best question, right? So, yeah, sorry about that, didn't notice. So front row, please.
Yeah, thanks for the call. You mentioned that YDB is an all-in-one database where you have the coordinator, failover, consensus, replicas, and I guess you've experienced an issue arising when the binary size is large. For example, ClickHouse with embedded everything release builds is around 1 GB. I guess YDB binary is even larger, and there come issues with the Linux kernel, like the memory pages get wiped out. It's not working as expected. So if you have experienced such issues regarding the binary size, text section, something like that, how do you resolve it? For example, lock sections of a binary in memory, you remap the executable to huge pages, something like that.
I think we don't find against this issue, but in general, we try to reduce our binary size because it's well known, the less binary size you have, the better software you have, the faster software you have. I'm not sure if it's completely related to binary size. It also might be related to quality of the code. But we indeed have a big binary, but I don't think we have issues with the size and with pages. But of course, we consider different options to increase our performance, and this one is important, but is not in the top of our list.
All right. Any others? All right. Well, gentleman over the green one, he was a microsecond faster than the second row there. So you will be next in queue. The gentleman in the green shirt, please.
You mentioned on the slide when you suggested YDB for cases that it's most suitable for read-heavy tasks. I didn't notice it, like it wasn't obvious from the previous slides when you showed the benchmark, because YDB was best in most of the cases. So maybe I missed something, but I didn't get why do you suggest it for more read-intensive, and is more write-heavy scenarios in your plan or not your priority? So it's like you are not designing it for such tasks?
Yeah, I completely understand your question because I was kind of vague. What I actually meant, because issues in CockroachDB and YDB, the comparison is not yet finished and not yet precise because you have update operation, you have upset operation, so you compare apples and oranges, and you can't with this comparison you can't be sure that YDB is indeed better in write operations here. Same about Yugabyte database. Because of their issues, they had also bad scalability of writes. And we can be sure that in upcoming release, the picture will not change. But we are very sure about our read results. And we are definitely faster than CockroachDB. It's completely faster, and we are sure that we will be faster than YDB in read operations. But still, we are sure that we will show comparable performance in writes. That is why we recommend read mostly loads of key value, but still YDB is great for write-intensive workloads. Also, it's maybe just a small note about YDB implementation and design. You know that there is almost behind every storage, there is LSM. It's implementation detail. And there are different options to implement LSM. You have size-tied, leveled compaction, and kind of everything has pluses and minuses. And we use size tired because it's slightly worse in reads because of read amplification, but it's awesome in write amplification. It has a very low write amplification. And yeah, at Yandex, we have a huge number of row updates. And to save disks, to have good performance, we take into account writes, but simply because of this particular research, we recommend read-mostly workloads.
Perfect. There was a question here at the second row, please.
Can you provide a scenario where EDB is not a better way? Some sort maybe of anti-pattern for usage of EDB?
We are not aware about such scenarios, but as a potential user, you might find this scenario. You can share this scenario with us, and we will fix it.
Maybe EDB is not best in working with big analytics data.
YDB is a OLTP database. It's not about analytics, but still we have relatively good analytical capabilities. So if you have OLTP database and you need to make some analytics, you don't have to use external database like ClickHouse. But in general, it's OLTP. And OLAP support is just to help our users to avoid using external databases. And also, I can share you some very secret information. There are some scenarios where we beat ClickHouse. But of course, just a small subset of possible scenarios of analytics.
Thank you.
All right, perfect. Of course. What could we expect otherwise? Our resident querier of the whole number 3 at the front row, please.
Now I got scared.
Yeah. Hi, I'm a query optimizer. So from the end user, if you will, / DevOps perspective, what settings suck in YDB? I mean, when you are faced with a brand new database, and YDB basically came out yesterday, you go grab a copy, you deploy it, and you get some of the settings wrong. For instance, there was a dreaded setting in MySQL regarding the, well, basically the buffer pool, the in-memory cache, which the default configurations always got wrong for like 10 years in a row. I'm kind of confident that there are, I don't know, top 1, top 3, top 7 mistakes that every external user is going to make. What should I do to avoid them?
Well, first of all, if you want to avoid mistakes when you set up database, you should simply choose YDB. Because it would be a huge mistake to not use YDB after today's presentations. But if you don't, I'm sure you will not make this mistake and you will use YDB. That's why you are asking the question. So if you use YDB, there are, of course, a lot of configuration options. But we try to make almost all configuration automatic. There is two kinds of configurations. First configuration is to set up YDB. And it might be a little bit long, and we do a lot of work to make it faster. But once you have set up YDB, it will just work like old German car.
So basically, there are no knobs and handles to turn. It should just power on and work.
Well, our goal
that's everybody's goal, right? Except it never works that way.
Well, let's jump to another example: spaceships. They are well tested and well configured, but they not always successful. We are like spaceship. Usually everything works smoothly, but sometimes
Houston die.
Yeah, but sometimes Houston we have problems.
All right. So bottom line, there are no knobs to turn and no usual de facto mistakes that every second user that tries out YDB makes. It's more or less automatic.
Yeah.
Okay,
In
thanks.
general, it's very automatic.
All right, problem solved. That was easy. So, last call for questions. We have time for one more. Right? Anyone? There's somebody in the middle or on the right side of the hall. Yeah.
You told that your system is multi-sharding, and you mentioned problem with consistent reads. So how have you solved that? Because of, for example, async replication. So
there is a problem with sharding in single server database because originally they haven't been designed for this purpose. And distributed databases are initially designed to be able to provide consistency, and they solve this problem in various possible ways. So we have implemented at YDB distributed snapshot. It can be persistent snapshot, or it can be done via multi-version concurrency control. So if I try to answer very shortly on your questions, one of the options is to use multi-version concurrency control to get consistent snapshot, consistent read. You might want to check MVCC talk. It describes our approach in depth.
Right, and here we'll have to step in and abuse my host powers, and the lines are closed. We are running out of time. So now the last task for you is remaining to select the best question, which in your view was the best from the audience, and they get a prize.
The man in green t-shirt.
All right, gentleman on third row with the green t-shirt, right? So you get the prize.
Also, he got many lottery tickets.
Maybe, right? So, excellent. A round of applause for our presenter.